Welcome to the lecture that includes atomic theory, mass, and isotopes. In our class lecture, we talked about the atomic theory of matter, where all matter is made of atoms, and atoms have electrons and protons and neutrons and all that in it. What we didn't talk about was kind of the history behind the atomic theory, how the atomic theory and all the parts of the atom and stuff were discovered. So we have to travel back to the 4th and 5th centuries BC, before Christ, in which Leucippus and Democritus lived. And here's some pictures of statues or representations of Leucippus and Democritus. And these guys were Greek philosophers who theorized that matter, everything that they saw and touched and felt, was ultimately composed of small indivisible particles. Okay, so back then they couldn't, they didn't have the technology or any kind of, further thinking on how to figure this out, but they just kind of theorized, all right, this rock that I'm feeling must be composed of smaller indivisible particles, and they call those atomos, okay, which is where we get the word atoms from. Now, it's not until 1808 AD, okay, so several centuries later, that formal, thinking and scientific processes and experiments could be explored in order to either prove or disprove this thinking of atomos or atoms. And in 1808, John Dalton, who is pictured here, okay, was pretty much the first to formalize that theory. He suggested that each element is composed of tiny, indestructible particles called atoms. Okay, basically he took that from Democritus and Leucippus. And he furthered that and said all atoms of a given element have the same mass and other properties that make them different than other atoms. Okay, so that was the second part of his theory. And the third part is that atoms combine in simple whole number ratios to form compounds. Okay, so what that means is that, to get the compound water, the atoms hydrogen and oxygen would always combine in simple whole number ratios. For example, H2O. It's always 2 hydrogens and 1 oxygen to make the compound water. If it was anything else or anything different, then it wouldn't be water. Same thing with salt. NaCl. One sodium and 1 chlorine atom combine to make the compound salt. So atoms are kind of combined in simple whole number ratios to form compounds. And all the atoms of a given element have the same mass and other properties and make them different than other atoms. So basically he's talking about each element has different kinds of atoms from each other. All right, about 50 years later, okay, we have this guy named J.J. Thompson in 1856. Lived from 1856 to 1940. Basically, he ran a lab. And at this time, they were, kind of the technology was there to be able to do some experiments. And so he discovered that atoms were not, solid, indestructible things. They actually were made of other stuff. All right, and the first thing that he discovered was that atoms had electrons in them, what they called electrons, because he did some experiments and he found that within atoms there was this negatively charged thing, okay, that were lighter and smaller than the atoms themselves. And he tested many different kinds of atoms or material with atoms and found them present in all of them. Okay, so he figured that these little tiny, very light, negatively charged things are in all atoms, okay, because he experimented on many different kinds of atoms. So he called these negatively charged small particles electrons. And he was English, and so popular English dessert is what they call plum pudding. And so he theorized or came up with this theory or this model called the plum pudding model, in which this negatively charged electron is held within positively charged sphere. And we have to put the positive there because they know from way back that all matter is electrically neutral. So if there are negative particles, then there must be positive particles to cancel it out. Okay, otherwise we'd have matter electrically attracted to each other, which is not the case. Okay, so we for example, if our bodies were electrically unbalanced, we would be constantly drawn and pulled toward things of the opposite charge. All right, so but that is not the case because all matter is electrically neutral. So his model was that these negatively charged electrons were held within a kind of think of like a jello-y positive sphere kind of shape. Okay. All right. So that was his kind of contribution to the atomic theory. Now, he had a student that worked with him who was Ernest Rutherford. He actually worked in J.J. Thompson's lab. And he did some experiments that are called the famous gold foil experiments, where he took a very ultra-thin film of gold foil and he shot little alpha particles at it, basically little helium atoms at this gold foil. And he had, in fact, down here on the bottom is kind of the setup for his thing. So we had the gold foil in the middle. This was the alpha particle shooter. So we shot it at the gold foil, and he had this detector ring, okay, around it to see where those alpha particles would go. Okay, so as he shot these little alpha particles through the ultra thin sheet of foil, he found that the majority of them passed directly through. Okay, but kind of as he hypothesized. Okay, but a significant amount of them actually deflected, and some of them even bounced back, which was peculiar because they at that time didn't think that atoms or anything inside matter was super small and tiny and dense enough to bounce anything back. So he hypothesized, after doing this for many years just to make sure that he was right, he hypothesized that matter is made up of actually mostly empty space that is dotted with dense little particles. Okay, because what was happening is that those little tiny alpha particles were bouncing off nuclei. Okay, we don't call it. He didn't call it those yet, but they were bouncing off the nuclei of the gold atoms that made up the gold foil and bouncing in different directions. Okay, in fact, his work was so significant because he kind of compared it to shooting a bullet at a tissue paper and the bullet bouncing back. Okay, so the results of his experiment were completely surprising to everybody. All right, so he basically found out that matter is mostly empty space because most of those alpha particles, went right through the gold foil. However, some of them bounced back. So among that empty space of matter must be these little dense, tiny little particles, which we'll eventually call nucleus. All right, so now the rest we covered in our classroom lecture, where we started off with the nuclear theory of the atom, with the most of the atom's mass and all of the positive charge are contained within the core, those dense little particles that Rutherford discovered called the nucleus. Most of the volume of the mass is empty space, and the negatively charged electrons are outside the nucleus, okay, in that empty space. So that part we covered in class. This was just kind of the part leading up to the nuclear theory of the atom. All right, so from the class lecture, we know that atoms are made up of protons, neutrons, and electrons. And the protons are positive and in the nucleus. The neutrons are neutral inside of the nucleus, and the electrons are negatively charged outside of the nucleus. And we also discussed that the protons are what makes the identity of the atom. If you change the number of protons, you change the identity of the atom. And we also talked about the periodic table, metals versus nonmetals, and some of the properties and periodic laws from that. So what we're going to get to next is what we call isotopes. Okay, so John Dalton wasn't 100% right in his atomic theory, where he said that all the atoms of an element must have the same mass and the same properties. Yes, they have the same properties, but we have found out that all of the atoms of a particular element don't necessarily have the same mass. Okay, that is because each element has different isotopes of atoms. Okay, so all atoms of an element do have the same number of protons. Okay, otherwise, if they didn't, they'd be different atoms from each other. But they don't necessarily have the same number of neutrons. Okay, so that's where we can have different masses. Okay, so all atoms of a given element do not have the same mass, like Dalton hypothesized. We see here, as an example, the element hydrogen. Hydrogen comes in 3 different varieties. It can have 1 proton and no neutrons. It could have 1 proton and 1 neutron, or it can have 1 proton and 2 neutrons. They are all hydrogen atoms, okay, but they are all going to have different masses, right? Remember, protons and neutrons are both 1 atomic mass unit, so this mass of hydrogen would be 1 atomic mass unit. Looks like a weird 7 here. 1 atomic mass unit. This one would be 2 AMUs, and this atom would be 3 AMUs. So remember, they're all hydrogen atoms. They all have 1 proton, which means it's hydrogen, but they have different numbers of neutrons, so they have a different mass. This is what we call isotopes. Atoms with the same number of protons but different number of neutrons, therefore a different mass. Here's another example of carbon, the element carbon. Carbon is made of, all carbon atoms have 6 protons, but we have different isotopes of carbon with different numbers of neutrons. Here is a carbon atom with 6 neutrons, here's 7 neutrons, and here's one with 8 neutrons. Okay, so remember, they all have 6 protons, but they have a different number of neutrons. So they're all the same carbon atom, they're just isotopes of each other. All right, so here's something about isotopes that you may or may not have learned before. For a given element, the relative amount of each different type of isotope in a naturally occurring sample of that element is always the same. It's what we call the percent natural abundance. Okay, so if we take a random sample of carbon from Africa and we take a random sample of carbon from Europe and a random sample of carbon from South America, they will all have the same percentage of isotopes of that element. So for example, if we do the carbon like we said, all carbon samples have 98.89% are of the carbon-12 isotope. Okay, only about 1% is of the carbon-13 isotope. And then obviously even less than that would be the carbon-14 isotope, which is actually radioactive. So the amount of carbon-14 in it will actually decrease over time. Okay, so that's no matter what. That's what we call the percent natural abundance. Whether we take, like I said, the carbon from anywhere in the world, if we analyze it, 98% of those atoms will be carbon-12, about 1% will be carbon-13, and even less of that would be carbon-14. Same thing with oxygen. If we gather a sample of oxygen atoms, from the air from different places around the world, we're going to have the same percent natural abundance for oxygen. 99.76% will be oxygen 16. Okay, it'll have 8 protons and 8 neutrons. And then only 0.04% will be oxygen 17, where it's 8 protons and 9 neutrons. And then 0.2% will be oxygen 18 with 8 protons and 10 neutrons. Okay, so that's what we call the percent natural abundance. It's how much of each isotope will be in a naturally occurring sample of that element. All right, so when we're talking about different isotopes of atoms, we can symbolize them in 2 ways. Okay, so this is what we call isotope symbols. We've got, you always put the elements symbol, okay, nice and big in the middle. All right, so here's the element symbol. And then up on top we have what's called the mass number, which is the number of protons plus neutrons. Okay, because remember, the mass of an atom is protons plus neutrons. Okay, so the mass number goes on top, and the atomic number, the number of protons, goes on the bottom. So if we see this example here, then of the different hydrogen isotopes, we can see how this works. So H is for hydrogen. That's our symbol for hydrogen. And we've got the mass numbers on top. All right. 1, 2, and 3. And the atomic numbers on the bottom. Remember, atomic numbers and number of protons. So on every isotope of hydrogen, the bottom number is always the same because it's the number of protons. The top number is the one that's going to change depending on the isotope, because the top numbers are going to have different numbers of neutrons. So hydrogen with a mass of 1 is not going to have any neutrons. Hydrogen with a mass of 3 will have 2 neutrons. Okay, so that's one way we can symbolize it. Another way, a more simple way, and maybe a more common way, is just to write out this element name or the symbol and have a little dash with the mass number behind it. So that's what we see here in the hydrogens. So instead of writing out, the big H with the 1 and the 1, we can just say hydrogen-1, meaning it's the hydrogen atom, the hydrogen isotope that has a mass of 1, versus this guy over here is the hydrogen atom that has a mass of 3. Okay, so that back number there is always going to be the mass number. All right, because we don't need to know the proton number because the number of protons for hydrogen is always the same. So the back number is always the mass, and we can subtract the mass number minus the protons to get the neutrons. All right, so here are some example problems for you to try. So pause the video and see if you can answer these questions, and then unpause it and check your answers. All right, so for the first one, it's what is the atomic number, mass number, and symbols of the nitrogen isotope that has 8 neutrons? Okay, so for the isotope symbol, what we're going to do is big N for nitrogen. Okay, if we look up on our periodic table, nitrogen has 7 protons. And if this particular isotope has 8 neutrons, that means that the mass is 8 plus 7, which is 15, and the mass number will go on top. Okay, so that's one symbol. Remember, the other symbol is just writing out the name, nitrogen. And we put a dash 15 for the mass. All right. Okay, second one is how many protons and neutrons are in the chromium isotope? Chromium, 5224. Okay, so protons are easy. Remember, that is always the bottom number. Okay, so protons is 24. Okay, now to figure out the neutrons, we have to do mass number minus the number of protons, right? To figure out the number of neutrons. So 52 minus 24 is going to give you the number of neutrons. So that's going to be 28 neutrons. All right, so hopefully you got those right. If you didn't, make sure you see me next class so we can go over isotope symbols a little more. All right, the last topic in this lecture is atomic mass. And the atomic mass is what we find on the periodic table. It's the number that we find, the decimal number we find underneath the symbols, okay, for the elements. It's usually always a decimal number because remember we just learned that the atoms of a given element may have different masses, right? Because there's different isotopes of the elements. So we can calculate the average mass, which is called the atomic mass for each element. And this represents the average mass of the atoms that compose that element. So it's the average mass of all the isotopes of that element. If we take the average, we will get that number on the periodic table. All right, so here is how it is calculated. Okay, whenever we're figuring out the atomic mass of a certain element, we must take into account the percent natural abundance for each isotope. Okay, remember that's the percentage of that isotope in a sample of an element. So what we do is we take the percent natural abundance for one isotope and we multiply that by the mass of that particular isotope. So, and then we add it to the percent natural abundance of the second isotope multiplied by its mass. We add it, if there's a third isotope, we take the percent natural abundance of that third isotope multiplied by the mass, and so on and so forth. So let's take a look at an example. So it says chlorine is made up of 75.77% chlorine 35, okay, which has a mass of 34.97 atomic mass units. And the other 24.33% is chlorine 37 atoms, which has a mass of 36.97 AMU. So what is chlorine's atomic mass? Well, we can see that it only has two isotopes. It has isotope chlorine 35, which is 75%, 76% of it, and we have chlorine 37, which makes up about 24%. So what we do is we take the 75% chlorine, and remember when we're doing percentages with math, we have to convert that to decimals. So we move it over 2 times to the left, so 0.7577, and we multiply that, so that was the PNA of isotope 1, and we have to multiply that by its mass, and it says its mass is 34.97, all right? So we're going to do that, and then we're going to add it to the percent natural abundance for isotope 2, okay, which is the chlorine 37, and that percent natural abundance is 0.2433, and we're going to multiply that by its mass of 36.97. Okay, so when we do that math and we add those two together, we will get the atomic mass for chlorine, which is 35.45 AMUs, atomic mass units. So that's how we get the number that's on the periodic table, that average mass of the element, which is what we call the atomic mass. So let's try one more example together. Magnesium has 3 naturally occurring isotopes with masses of 23.99, 24.99, and 25.98 AMU, and a natural abundance of 78.99%, 10%, and 11.01%. calculate the average mass of magnesium. All right, so here we go. Remember, the average mass is going to be the PNA, percent natural abundance of isotope 1, times its mass of times its mass, right? Plus percent natural abundance of isotope 2 times its mass, plus, in this case, there's 3 naturally occurring isotopes, so we're going to do it one more time. Percent natural abundance of isotope number 3 times its mass. Now, a lot of people are like, if we're doing the average of blah, 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 and shouldn't we be dividing it by 3? The answer is no. We don't divide it by 3 because we are already taking into account the percentages of each isotope within the calculation itself. So we don't need to add these all together and then divide by 3, okay? Because we are already taking into account the percentages within our calculation, okay? Now, if we weren't given, for example, if we weren't given the percent natural abundances and we had to kind of take an average of these 3 numbers to figure out, exactly what it was, what the average atomic mass was, then we would add all 3 of these up and divide by 3. But since we're given the natural abundances, okay, we can put that into our calculation and make it more exact. All right, so that's exactly what we're going to do. We're going to take the percent natural abundance of isotope number 1, okay, which is 78.99. Okay, and remember we need to convert that to percentage decimals. Okay, so we're going to move that decimal over 2 times to the left. So 0.7899 times its mass, 23.99. And we're going to add it to number 2, okay, which its percent is 10%. So we're going to put 0.1000 because we got some sig figs there. Okay, times its mass, which is 24.99. And we're going to add that to the third one, okay, which is its percent natural abundance is 11.01% times its mass, which is 25.98. All right, so when we do all of that math, we're going to get the average atomic mass, okay, of magnesium. So the answer is 24.31, okay, is the atomic mass for magnesium, okay, all of the magnesium, for the entire magnesium element, okay, taking into account the percent natural abundance of all the different isotope atoms of magnesium. All right, and remember, we always have to do sig figs, okay, so keep that in your mind. Why is it 24.31 and not just 24 or 24.3 or 24.309099? Okay, remember it's sig figs. We got to look back to the numbers that we start with in our equation. In our question. Okay, so of all these numbers, how many sig figs are there? Well, there's 4 of them in each of those numbers, so that means our answer should have 4 sig figs, and it does. At 24.31 is 4 sig figs. Okay, so we can kind of check off our sig figs and make sure that we are correct. And we can also check our answer by taking a look at the periodic table. If you look at the periodic table for magnesium, the average atomic mass indeed is 24.31. If you got anything other than 24.31, it may be that when you put it in your calculator, you're not using your parentheses. It's super important to use the parentheses in the calculator. Otherwise, the order of operations might be wrong in the way that it calculates it, and you may get a wrong answer. So just an FYI, if you don't get the correct answers for these and you're wondering why, you're plugging in the numbers all right, use the parentheses. Okay, that way the order of operations is done correctly within the calculator. All right, here's the last slide for this lecture. And it is another problem for you to try on your own. And in fact, it gives you the answer down there for your reference. I am not going to go over this one. If you did not get this answer when you did it on your own in this space provided, then make sure you come see me next class so that we can figure out why.